Hello everyone. So this video is about linearization. As we've seen in the previous videos that after the optimization either through Hamiltonian or the Lagrangians, we ended up with non-linear difference or differential equations. It is because of this reason that generally there exists no closed form solution for these equations. So what we do is that we rely on some numerical approximation techniques to solve those equations. So we'll look over some of these techniques in a broader sense that are often used for this purpose. Taylor series is at the center of this, so we will start with the Taylor series or Taylor expansion, which says that we can write a function around a particular point A such as a power series of the form where f of x is equals to f of a, where a is, well, the value of a could be any value of x. So we could write a function around that point a such as f of a plus f prime of x evaluated at point a, then x minus a divided by 1 factorial plus on and on. So this is a Taylor expansion where a is a point around which we want to evaluate the function. Let's see an example for this. So let's say we have f of x as 3x squared minus 2, and we want to approximate this function value around 0. How we will do it is that, so let's just find out the terms that we need for this, and let's just compute f of a, which is the function evaluated at point a. At the a is 0 in our case, so we have f of a as minus 2. Then let's just compute the second term, which would be f prime x, and when we will evaluate f prime x at point a, we will get, where a is equal to 0, we will get this f prime a as 0. The second term would be f double prime x, we have 6, and then f double prime a would be 6 itself because there is no x in here. F triple prime x would be equals to 0, so f triple prime a would be 0, and afterwards since every differential will be 0, so the value of that differential at point a would also be 0. So we can proceed and substitute those values into this Taylor expansion, and what we get is that f of a is minus 2 plus f prime a is 0, then x minus a or 1 factorial plus f double prime a, which is 6, x minus a squared divided by 2 factorial plus, and we will write the further terms that we so we simplify this, and what we get is the function itself. And the linear approximation of Taylor theorem is that if we just include these first two terms, it will give us a good enough approximation of the original function itself. In economics, the a, which is over here, is usually the steady state value of that variable. It's the steady state that we discussed in the difference or differential equation case. So x minus a over here, x minus a will be the deviations from that steady state. So we assume that variable converge to their steady state in the long run. So in the long run, those deviations will be 0. So what we mostly see is the case for a single variable, and for a single variable, this Taylor expansion, first order Taylor approximation for a variable x of function f of x would look like this, where x star over here is just like a. We're just saying x star is a value, is a steady state value around which the function is evaluated. F prime x star is the first derivative of that function evaluated at x star, and we have x minus x star. Of course, it's divided by 1 factorial. Since 1 factorial is 1, we can omit it. For two variable case, first order Taylor approximation, first order Taylor expansion would look like this. If we have a function which includes two variables, we will write it as this form when we want to do the first order Taylor approximation. So let's just go and take an example of this linearization. So let's just do a log linearization. It is the first of the method that we are going to study. So there are different methods for this linearization. The first and probably the universal method is the which uses the Taylor expansion as it is. We call that log linearization. And through this method, so we'll do this method first, and then we will see some of the shortcuts which in turn are based on this method, but they are easy to use. But for exposition purpose, we'll start with that. So let's just take the example of a production function. The production function is, we know, yt written as kt raised by alpha, lt raised by 1 minus alpha, where output is non-linearly related with capital and labor. The first step is to take the logs. We take the log and we reach to this expression. And the second step is to do the first order Taylor approximation of different functions over here. So we have variable yt, kt and lt. So we will do the first order Taylor approximation for log of yt, log of kt, log of lt, and then we will substitute those in this equation. So let's just do first order Taylor approximation of log of yt. So let's just understand how we achieve to this first order Taylor approximation for the function log of yt. Again, so the same process we will follow for this log of kt and log of lt. So let's just understand it and step by step. So let's just keep in mind that underline what we have is that we have a function. We are going to evaluate that function at a steady state, plus we will take the first differential and then we will evaluate that first differential at the steady state, and then there would be this term where we will have that variable minus the steady state. So what do we have as a steady state for this variable yt? So at the steady state, we know that the variables don't change, so the time t would drop out. It means they would reach to a certain value and they would remain same on that value. So there will not be any change. So yt would be equals to y. As we saw in the case of difference and differential equation, that yt is equals to yt plus 1 is equals to yt plus 2 is equals to a certain constant. So let's just say in that case it is equals to just y itself. So a would be equals to y in our case. So let's just evaluate this function at this value. So we have L log of y of t, and at a is equals to y, we will have log of y evaluated at value a at a steady state. Next is that we have to find the first differential of that function. So the first differential for that would be log of yt would be 1 over yt. Again, now we have to evaluate it at its steady state, which is yt is equals to y. So when we will evaluate it, what we will get over here, 1 over, so 1 over y, it should be 1 over y when we will evaluate it. So what we will get over here is that if we evaluate this first difference at yt is equals to y, we will get 1 over y. So now we have all those terms. We'll just substitute it over there, and this is how we got log of yt is equals to log of y, which is nothing but this term, plus 1 over y, which is nothing but this first difference evaluated at steady state into this deviation from the steady state. First order Taylor expansion. So we did the same process we will do for log of kt. We will achieve this function, and the same process we will do for this function log of lt, and we will have the same expansion as this. So the first step was to take the log, second step was to do the first order Taylor expansion, and then we will substitute those into this function, this expression that we had at the start. Instead of log of yt, we will write this expression. Instead of log of kt, we will write this expression, and instead of log of lt, we will write this expression. So we substitute that. One more step that we have to do is that we have to substitute the steady state condition into this expression. So we know that at the steady state variables don't change. It means that they will reach to certain constant, and once we substitute that value in here, we notice that once we substitute yt is equals to y over here, this term will drop out, this term will drop out, and this term will drop out. So once we substitute this steady state condition, we are left with this expression, which is log of y is equals to alpha log of k plus 1 minus alpha log of l. As the last step, we have to use this steady state expression into the original equation, which is over here. So what we will get is that once we substitute this over here, it means we can cancel out log of y, alpha log of k, and 1 minus alpha log of l. So what we will be left with are these expressions only, multiplied by alpha, and this expression multiplied by 1 minus alpha. So notice that yt minus y over y is the percentage deviation of y from its steady state value, which is y, as we saw earlier, as we assumed earlier. So the percentage deviation in that variable are related with the percentage deviations in with capital and labor through this form, which is linear. So we started with a non-linear production function. We finally ended up at a linearized version of it, where we represented that variable as a percentage deviation from the steady state. If I just represent those percentage deviation with this small letter and with this tilde sign, that sign you're going to see a lot in macro course, and so I can just write this equation in this form, where the percentage deviation in variable y tilde t, so there has to be a small t over here. Let me just add over here. So there is a small t over here equals to alpha kt tilde plus 1 minus alpha lt tilde. So percentage deviation in y are related to capital and labor in this form. So with that, this is the one method. The next method we're going to see, it uses some of the shortcuts, and slightly easier to manage, especially for complicated expressions. So we'll see that. Okay, so we are going to see some shortcuts for the linearization, the log linearization method that we just saw. And so we started with the production function. We're going to carry on with that. We're going to use just slightly different method, and we'll end up with the same equation. So let's just kind of assume that this small xt is a variable. If we want to represent that, represent the percentage deviation from steady state of a variable, we can just write it in this form. We know that the percentage deviation from a particular value can be written as this as well. Log differences are percentage deviations. If you want, we can drive this as well, but let's just take it as a given that the log differences are this expression is equals to this. So let's just proceed with that, and let's just look at some of the shortcuts. The first shortcut is that we have xt given equals to x, which is the steady state value, e raised to the power xt tilde. Xt tilde is this. Again, we are sort of taking this as a given. If you want, we can drive this as well. This would be coming from this expression. If we just take the exponent of it and use the steady state condition, we will just reach over here. Instead, if we just take the exponent of this expression, we will reach to this expression. This is nothing but just in exponent form. The second shortcut that we're going to use is that e raised to power xt tilde would be equals to 1 plus xt tilde. We can again drive this expression. This would be first order Taylor expansion of e raised to power xt, but let's just take this as a given. So we're going to use these two shortcuts whenever we want to do the log linearization. So wherever there is a variable, we can either substitute this as this, and whenever we have e raised to power xt, we can substitute for this. So let's just use these two expressions and log linearize this production function. So again, the steady state, at the steady state we know that the percentage deviation from this equilibrium value would be 0. So the deviations would be 0. At the steady state, the variable would reach to its steady state. At the steady state, xt would be equals to x. That's why they would not be, the xt tilde would be equals to 0. Okay, so with these shortcuts, let's try to log linearize this production function. Instead of yt, I can write down y e raised to the power small y tilde t, and instead of kt, I can write down k e raised to the power small k tilde t, raised to the power, whole raised to the power alpha. So let's just do that, and we got these expressions. Next, we have to just simplify this expression and then use this shortcut as well. So I can just separate exponent terms. So I can write down k raised to power alpha, l raised to power 1 minus alpha, and then this alpha will be multiplied with kt. I can write down e raised to the power alpha kt alpha kt tilde, and then same would be for this case. The next term, we just want to add up the exponent terms together, and over here we are good to use this shortcut. So this whole term we will write it as 1 plus, because we are using this shortcut. E raised to power xt tilde is equals to 1 plus x t tilde. So whatever we have in the exponent term, we'll just add 1 with that and we can expand it. So same we will do for e raised to power yt tilde, and then e raised to power this whole term. All we have to do is to just add 1. After we reach to this expression, the next thing that we have to do is to apply the steady state condition. And the steady state condition is that we know is that at the steady state, those deviations from the equilibrium value would be equals to 0, or this tilde terms would be equals to 0. So once we apply the steady state, what we get is, after this simplification, what we get is this term will drop out and this whole term will drop out. So what we will get is only this term and this term. So after applying the steady state condition, this whole equation will be reduced down to this expression. So the next step is that we will use this steady state condition into this expression. Once we use that, these two terms will cancel out and we will be left with this expression. Again, we can apply the steady state condition over here. We know that k raised power alpha l raised power 1 minus alpha is equals to y. We can cancel these terms, y with k raised power alpha 1 l raised power 1 minus alpha. So what we will get is, we will have y t tilde. There is a small t over here and over here as well, which is equals to alpha kt tilde plus 1 minus alpha lt tilde. So we have those small t over here, and we reach to this expression. As you can notice that this expression is same as we had earlier, as we saw earlier, but this expression is slightly, but this method is slightly easier to solve as compared with the last method. So we started with production function and we reached to the log linearized version of it, which is linear, of course, and using two methods. And this same shortcuts and this method you would be using to log linearize all those first order conditions that you will drive after the optimization process. And then there would be some other methods eventually that you will see that you would need to solve those log linearized versions, and then that you will solve the model. With that, I think we can stop over here. Thank you.